Welcome to Manchatmosphere. Today I'm going to have a chat with Professor Hugh Coe, who is a Professor of Atmospheric Composition at the Centre for Atmospheric Science at the University of Manchester. Welcome to Manchatmosphere, Hugh.
Thank you, Adil. Hello.
Professor Coe will have the opportunity to respond to only 5 questions. So Hugh, what aspects of atmospheric science are of interest to you?
So I study atmospheric particles in the atmosphere. Particles are tiny little things, 10 times less than the width of a human hair, and they populate the atmosphere all over. They range in concentration from background of only 100 particles per centimetre cubed to, in polluted areas, 1 million particles per centimetre cubed. They're formed from natural sources, sea spray, desert dust, volcanoes, and pollution, man-made emissions from car exhausts, from biomass burning, from agriculture. And those particles interact with light in the atmosphere, they interact with clouds in the atmosphere, and they have a big impact on human health. So I'm interested in their life cycle and how their effects relate to climate, to weather, and to air quality.
What specifically makes your research unique in your field?
So, over many years, my group has built the capacity to measure aerosol particles with very high precision on the ground and from aircraft platforms. We're able to measure their size, we're able to measure what they're made of, we're able to measure how they mix with things, we're able to measure how they interact with clouds. In the UK, that's a unique capability, and it means that we can address some major science issues that really no one else can.
So what methods do you employ to execute your research objectives?
So, we have a range of instruments, including mass spectrometers, where we can measure the composition of individual particles or the composition of the bulk of a number of different particles. We can charge particles and put them through an electric field and measure how much they're deflected, and that tells us how big they are, and by counting the numbers as a function of the voltage that we expose those particles to, we can measure the size distribution. We can use absorption photometry, so we can put these particles through a laser beam, and if they absorb, if they contain black carbon or absorbing material, they're heated. The coatings are evaporated, and we can then heat the core until it incandesces, it burns, and we can measure the intensity of that and relate it to the amount of the absorber. So we can do all of these things and measure the properties of these different particles, and that tells us a lot of information about the particle, and then we can use that to infer how it behaves in the real world.
Why is your research relevant in the wider world?
Aerosol particles have a big impact on human health. There are health estimations that there are deaths resulting from particle exposures, so premature deaths, that's to say people have died earlier than they otherwise would have done as a result of exposure to particulate in urban environments. And estimates are of the order of about 23,000 people a year are thought to die prematurely as a result of that exposure. That's very uncertain science, so we need to understand that and the ramifications of that rather better than we currently do, and provide the causal links between the emissions and that exposure. On the climate scale, we know that particles scatter radiation back to space, and that to some extent offsets the effect of warming by greenhouse gases, notably carbon dioxide. But some particles, like black carbon, absorb that radiation and so heat the atmosphere. that adds to the warming by the greenhouse gases. Particles aren't as well distributed around the atmosphere as greenhouse gases, so they tend to have regional effects rather than global effects. We need to understand those, and the uncertainty there is rather high, and our predictive capability is rather poor, so we have to be able to understand that. Particles act as sites for cloud droplet formation, and also the formation of ice nuclei, ice particles in the atmosphere, and that affects the cloud properties. If we have many more particles, then we distribute the water that forms as a result of a cloud forming across a greater number of particles. That makes the cloud brighter than if the same amount of water was on only a few particles. So the top of the atmosphere is brighter and the surface is cooler if we put more pollution in there. That clearly has an effect on the climate and the radiation balance. But that's again very uncertain and not very well captured by climate models. All of those things are important potentially, and we need to understand them, understand their physical bases, and then scale that physical understanding up to be included in a model that has predictive skill, and that's kind of what we do.
Finally, I'd like you to give me one exciting fact about your atmospheric research.
Well, I suppose the fact is that out in the urban atmosphere, particles of 10,000 or 100,000 particles are in every centimetre cubed. When we inhale that, we breathe in 1 or so litre of air a minute in each breath. That's going to give us something like 10 to the 6, 10 to the 7, 10 to the 8 particles in every breath. So that's something like 1 million to 100 million particles with every breath we take when we're out there on the street.
Well, thank you, Professor Hugh Coe. It's been a pleasure chatting to you on Manchatmosphere.
Thank you very much.